Okay, chapter 12. Continuing with chapter 12, this is a slide that we ended the previous lecture session with, so we'll move on to the next slide. This chapter was talking about scaling and things of the sort. This particular slide is referring to the fact that depending on your style of architecture, you can have varying degrees of weight in the roof or ceiling. So, if you look at a lot of the old, I forget whether this is Greek architecture or Roman architecture, where you can see that they have flat roofs. Can you see that the roof has fallen in? Right? So basically a lot of times if you have either flat pointy roofs or flat roofs, what happens is that over time as the mortar, the cement between the block, sorry?
It's a Greek building.
That's Greek? Thank you, extra credit to you. Right? So the mortar between the blocks, that gets eaten away with rain and sun and so forth, and after a while what happens is the flat blocks just fall through and the ceiling basically falls through. That's one. The second point is that notice the number of these pillars that are necessary. Like in a structure like this, you need a huge amount of pillars inside as well as outside, like inside the building as well, to hold up, to support the roof. If you change the style of the architecture, first, instead of flat roofs and so forth, now if you go to these curved arches, what happens is in the curved arch, you have blocks that are placed horizontally, and then here vertically, notice that this, the keystone, notice that the stone is not parallel faced, it's slightly tapered, right? So the stone is wider at the top and narrower at the bottom. Now what happens is, in the case like this, the weight of the stone, pulling the stone downwards, actually locks all of these, the arch. The more the stone settles down, the more everything gets locked in place. So a little architectural change like this, instead of having, for instance, horizontal arches, if you will, right, horizontal doors and so forth, or supports that are horizontal and vertical, changing like this makes this much more durable. The other thing is, if you were to change the shape of the roof to a hemisphere like this, now what happens is you can have a much larger area inside the hemisphere, under the roof, without having to have supporting pillars in the middle. So you could have a big round like hemispherical roof like this and no pillars inside supporting up the roof. And the reason for this is because with the hemisphere, the weight of the hemisphere, instead of coming directly, if you look at this flat roof, what happens is the weight of the tiles in the center are coming directly down here. So you have really strong supports. With the old architecture, you'd have to have pillars in here. Now we're able to do it because we have beams of metal and stuff, right? In the case of a hemisphere, what happens is the way the hemisphere is shaped, the weight of the hemisphere is distributed down the curve to the periphery. So you need a bunch of pillars along the periphery, but the weight is not pulling the roof to collapse in the center of the hemisphere. So the phenomenon here is kind of similar to the situation here, where the weight is actually distributed down these towards the left and the right as well. Okay, so the idea behind scaling, the whole field of scaling, is to study how size affects the relationships among weight, strength, and surface. Do you think it's possible to create a cockroach that is the size of a human being?
Create a what?
A cockroach? A roach? The size of a human being? Or a butterfly the size of an elephant?
Somebody would have done that.
Sorry?
Somebody would have done it already.
Okay. So you're basically saying no.
Are you talking about like...
Just take a cockroach, a roach, and scale it up.
Can you take a real cockroach
Yes.
and make it the size of a human?
Yes. Breed it. Breed it for bigger roaches until you get to the size of
over
a
a very,
human.
very long time. One person will not be able to do it.
Okay. Like a whole series of people over...
Over centuries.
Would anyone disagree with that statement? Without, I'm saying, you do this without diametrically changing the architecture of the roach. So basically take the roach and you scale it up. Make every part of it bigger. Would not work. Why not?
Well, because even if you made it larger, its mass would proportionally increase. It wouldn't have the same strength larger as it would when it was smaller.
Okay. Extra credit to both of you, right? And that is correct. What happens is, that insects have exoskeletons, right? So the skeleton is on the outside, and inside it's all gooey mess, right? Internal organs and stuff. Now, what happens is if you scale this, a roach to the size of a human being or a roach to the size of an elephant, what happens is there isn't sufficient support for all the internal organs and so on. The roach would just be in a puddle, unable to do anything,
But
right?
if everything's changing proportionally, wouldn't it be, like I read in the book that like an ant, its legs wouldn't be able to support itself. But if the legs are changing proportionally, then it still would be able to hold itself.
If you just scale it one for one, the answer is no, it wouldn't work. So scaling is about, we will see this as we go in further, maybe see this as we move to the next few slides, is you would have to, you can't simply scale up the volume. You'd have to change the proportion of volume to cross-section of the leg and that kind of stuff, right?
So it's not like a recipe where you just, if you double the recipe, you just do a half and half.
Beautiful example of scaling. Extra credit to you. So an example of natural scaling, this would be evolutionary scaling as opposed to revolutionary scaling. I'm just coining a couple of terms. Or microevolutionary scaling, right? Would be you just if you're making a cake of a certain size, you use so much dough, so many eggs, and all that kind of stuff. If you want 2 cakes, you just or a cake that's twice the size, double everything. If you want 4, quadruple it. Make one 10 times, make it 10 times, right? And typically with making a cake, that shouldn't be an issue as long as you mix everything properly and you've got reasonable ovens and all that kind of stuff. However, with creatures, that's not the case. You can't just take an object and scale it up. You can scale it up to a certain extent and then it'll just die. You have to completely change the architecture. So it's not an evolutionary process, it's a revolutionary process. Like some completely new information needs to come into the system. A completely new design has to come in to enable it to happen. So that's where, as you go up into the vertebrae and so on, you switch from an exoskeleton to a what? Yep. You switch to an endoskeleton. Exoskeleton.
Well, I was just thinking about there's some human beings that are much larger than they're supposed to be because they have some disorders or whatever, and you find that they don't live as long and they have a hard what?
We're present in the room. We are big.
They're really big, but they have trouble physically, like walking and just so. Isn't that an example of that? I mean, they're the same, but they're larger, but it doesn't work.
Well, what about ancient people? Like I just spent 3 weeks in Europe over summer, and it's got like all the history there. And I mean, those dudes were tiny back. You know, like being 5 feet tall was like a big dude.
Okay.
But now we've grown to be bigger than that.
Can I put a pause on my answering this question? And I'll answer the question a little bit when...
Sure.
Okay? But you're on the right track. We cannot take a human being and create a giant, like just by just normal scaling. We couldn't take a human being, a giant in the sense of, like if you look at the Harry Potter movies, the Trolls or whatever, like you can't build a human being that's 3 stories tall. Simply, you have to completely change the architecture of everything. You have to put in more internal scaffolding for the internal organs and all that kind of stuff. Which simply, even if you made us bigger, because we're hollow inside, right? Like in the sense, you've got the body, the bone cage. Then as you make this bigger and bigger, you've got a bunch of internal organs that are just dangling from muscles. So if you get big enough, you simply cannot sustain. You can't hold up the weight, so you have to change the architecture. But we'll come to that, right? So I'm putting a hold on that, answering that question. Okay, good question, extra credit to both of you for speaking up. So continuing with the concept of scaling, consider 1 cubic centimeter cube, right? 1 centimeter by 1 centimeter by 1 centimeter. So each of the lengths, X, Y, okay, X, Y, and Z, each of which are 1 centimeter. So that's the 1 centimeter cube. Now, if you scale this up to a cube that's 10 centimeters long, you take 10 of these, that's a long line, right? So along one dimension, 1 cube became 10. Now, if I put another 10 along the side and complete the square, how many cubes do I have?
1,000.
Let me rephrase the question. I have a line of 10 here, I have a line of 10 there, and I complete the square.
Oh, 10. 100.
Yeah, 10 multiplied by 10, right? So that's in 2 dimensions. Now, if I extend it to the 3rd dimension, I put 10 cubes along the z-axis and complete the cube.
1,000.
1,000, right? 10 multiplied by 10 multiplied by 10 gives me 1,000. So 10 to the power of 3. What if I were to extend this into the 4th dimension and create a 4th dimensional cuboid? Let's call it tesseract, based on this single cube. How many cubes would I have? 10,000. And if I were to do this in the 5th dimension, up to 5 dimensions, good job. You see the progression, right? 10 to the power of the number of dimensions that I'm doing this in. Not to say that we can physically do it, right? But at least mathematically we can imagine all kinds of things. Okay, so the question is, what is the volume of the scaled up cube? It becomes multiplied by a factor of what?
3.
How much?
A third. 10
Yes.
times 10 times.
Yes. The volume of the scaled up cube is 10 multiplied by 10 multiplied by 10 times the volume of this cube. So it's 10 to the power of 3, which is 10, which is basically 1,000, right? How about the cross-sectional surface area? How much did it go up?
10 to the 2.
Yep, 10 to the 2. So 100. What about the total surface area of the cube? Okay, total surface area. Now the total surface area, in this case we're looking at the outer faces, right? What is the area of this face? 100 centimeters square. Area of this face, 100 centimeters square. Of the top face, bottom face, the missing faces, there's a total of 6 faces. So what's the total area? 600 centimeters square. What is the total area of this cube? Surface area of the cube? 6. Up?
Oh, 6.
6. Because there are 6 faces multiplied by 1 centimeter square, right? So the 6 became 600. So you can see the total surface area went up by a factor of 100 for the entire cube. So similar, the scaling proportion is similar to that of the cross-sectional area. So here's an example. You take up a new cube like this, 1 centimeter by 1 centimeter by 1 centimeter cube. The surface area of the cube, you can take this and open it up, right? Like a box, like a cardboard box. You cut the sides, open them up, and here you end up with this cross with each of these squares here. Add them up. How many squares do you have in the cross? 6. And the area of one of these is 1 centimeter square. 1 centimeter multiplied by 1 centimeter. So the total surface area is 6 centimeters square. The surface to area volume ratio is 6 divided by 1. Now let's say I double the length, one side of the cube. This becomes 2 by 2 centimeters, right? So the same cross became bigger, except this is 2 centimeters by 2 centimeters. So if you look at the volume of the cube now, it's 2 multiplied by 2 multiplied by 2, right? So it's 8 centimeter cube. The surface area is 6 multiplied by the area of one of these, which is 2 multiplied by 2, so that's 4. Multiplied by 6 is 24. That's where you get this, right? Stop me if you need me to.
I'm totally lost.
Okay. Extra credit to you for speaking up, for saying that. If I were to take this cube and extend its side and make it 2 centimeters long, right?
Right.
The x dimension becomes 2 centimeters, the y dimension becomes 2 centimeters, the z dimension becomes 2 centimeters.
But, okay, I'm kind of slow. I don't
Not at all.
understand why
Mhm.
the surface area isn't 6 centimeters. Why is it 6 centimeters squared?
Oh, I see what you mean. You're on the first
Yeah,
example. The surface area, and your question is why is it 6 centimeters?
squared. I understand why it's 6 centimeters because each block would be
Okay.
a centimeter. Or one times 1 because you're doing it by either side. I got it.
Okay. Oh, do you get it?
I think so, yeah.
Okay. So the units of these dimensions. So here's the magnitude. The units are centimeter. So it's 1 centimeter, 1 centimeter. So the surface area is equal to, let's call this A and let's call this B. Surface area, or let's call this X and Y, right? That's X, that's Y. Will be X multiplied by Y. That's
Okay.
equal to 1 centimeter multiplied by 1 centimeter equals 1 centimeter squared. Right?
Yeah.
So the key thing is to remember that you have to multiply the units as well.
Okay.
So if you take this and you extend this to form a cube, then it's 1 centimeter, and whatever dimension is missing, 1 centimeter. So every one of them has a centimeter attached. So the volume equals x multiplied by y multiplied by z in terms of the dimension. So it's 1 centimeter multiplied by 1 centimeter multiplied by 1 centimeter equals 1 centimeter cube.
Okay.
That's where the units are coming from, right?
And the volume is basically the space inside.
Exactly. Yes. So definitely extra credit to you for speaking up and asking that. Okay, remember, if you have a question, if you don't understand something, there's bound to be somebody else in the class who doesn't get it either, who doesn't have as much courage as you do to ask the question. Okay, so when I change the length of the side, instead of 1 centimeter, now it's 2 centimeters, then the volume becomes 2 centimeters multiplied by 2 centimeters multiplied by 2 centimeters. So that's where this comes from. 2 multiplied by 2 multiplied by 2, that's 8 centimeter cube, is the volume of this cube once I make it proportionately larger by a factor of 2 in terms of the length. If I cut this bigger cube up and create the corresponding cross, the area of each of the faces is 2 centimeters multiplied by 2 centimeters, which is 4 centimeters, multiplied by the number of faces, which is 1, 2, 3, 4, 5, 6. That's where the 6 multiplied by 4 gives me 24 centimeters squared. So this is, if you just add up the areas of each of these cubes, I mean the squares, just like we did here, to get a surface area of 6 centimeters square, do this for the 2 centimeter sided cube, you'll end up with 24 centimeters. If I make a cube that is 3 times as large as that one in terms of the dimension, so this is now, one side is 3 centimeters multiplied by 3 centimeters, the area of one of these squares is 3 multiplied by 3, which is 9 centimeters squared. So the total surface area is 9 multiplied by 1, 2, 3, 4, 5, 6. So 9 multiplied by 6 would be 54. So the surface area is 54 centimeter square, and the volume becomes 3, which is one side, multiplied by 3, the second side, multiplied by 3, the third side, which is 3 times 3 is 9, times 3 is 27 centimeter cubed. So if you look at the surface to volume ratio of the first cube, you get 6 divided by 1. Surface area of the second cube, in this case, is 24 divided by 8, the numbers from here, which turns out to be 3 over 1. So you can see the surface area has become smaller. The ratio of surface area for a given volume is smaller for the larger cube compared to the smaller cube. If I go to even larger cube, the surface area is now 54, volume is 27, divide, and becomes 2 to 1. So you can see the progression. As the cube becomes bigger, the surface area to volume ratio gets smaller. There's less surface area per unit volume, we assume.
So will it ever get to a point to where the volume exceeds the surface area?
Where the volume...
Where the ratio between surface area to volume would be surface area 1, volume would be 4 or 5? You understand what I'm trying to say?
Yeah, that's instead of a ratio like this, you're inverting this.
Exactly. Would
Yes.
it ever get to that point?
That's a good question. Nobody's asked. There's one reason why I teach, right? Questions come up that I've never ever considered. My guess is the answer should be yes.
That's what they do with like,
Piece of paper,
well, if you take the,
right?
pens
Piece of
and
paper.
folder on a computer, that's what they're doing, they're decreasing the volume, so it fits the box, but increasing the surface.
Yeah. So,
Each bin has its own surface area,
so if you took a shape, if you convert this box into a sheet of flat paper, right, or aluminum foil, I would guess that the area is so much greater compared to the volume that you could end up with a situation where the volume, the number in the volume, the ratio is lower. Am I going in the wrong direction? I'm
Yeah.
increasing this. I'm going in the wrong direction. So
Yeah, so that was kind of...
that would actually make it worse, right?
Right.
Yes, I'm
Like-
going the wrong direction. So the short answer to your question is I don't know what the answer is to your question. Extra credit to you if you look it up. My guess is the answer is no. Right?
And so isn't that why this whole example here is why you can't make us bigger is because our cells are the surface, the volume, the surface area. So the larger the volume is, or hold on.
Mhm.
So you're going to talk about it right here.
Thank you for the segue.
No problem.
Right? But extra credit to you. Yeah, it is true that. We'll look at this and then we'll come back to that question, right? Which looks more like a sphere? An elephant or a snake? An elephant, right? Elephant is shaped more like a sphere in general, right? Big, round, legs sticking out. A snake, on the other hand, is kind of long and skinny for the same volume. If you were to take the volume of an elephant and make it into a snake, which is likely to have more surface area? Snake. Of the different shapes, the smallest surface area for a given volume is that of a sphere. The closer you look like a sphere, the less your surface area, right? Compared to a snake, really long, skinny object like this. If I were to take this object, look at all of its surface area, it's pretty large. If I were to squish it all together and make it into a tiny little ball, what will happen is it's the minimum surface area that that volume could possibly have.
You're saying, okay, so you're saying surface area to volume ratio.
Yes. So then the question that one of you asked just a moment ago, we can answer what's the minimum ratio by looking at a sphere, right? So, okay. So this is just making the point that because the elephant as a whole, for its mass, has a much lower surface area, that's the reason why, one of the reasons why its ears are so large. That the ear kind of thin and wide, what happens is the blood vessels through the ears help the elephant to cool off. Because there's more surface area, right? You know how you cool off, right? Blood vessels near the surface of your skin, basically you perspire and right? Heat is emitted from you as the liquid, the water evaporates. So allegedly that's what the elephants used to, that's why they have this big, huge ear. Of course there's a couple of additional reasons. Elephants can hear very low frequency, long wavelength waves, and the larger the ear like this, the lower the frequency you can hear. And there's a third reason, of course, is that when elephants need to slide, that's the other reason why they have to have large ears, right? Now this is making the point that this particular monkey has a really long tail. And the tail serves a couple of purposes. One is to hold on to branches and stuff like that, but the other one allegedly is also to radiate heat. Again, long, skinny, right, means more surface area, which means the object cools off. Now, not meaning to be politically incorrect, in my experience, friends of mine who are long and skinny tend to get colder sooner than chunkier friends. Now, there's a small possibility that this may be linked to that. Another possibility is, which I think is more likely, is really insulating that layer that's present when we get chunkier. Right? Okay. So let's go ahead. Oh, okay, let's look at the first question. This gives you an idea of the kinds of questions that we could deal with. What cooks faster in boiling oil? A sliced potato or a whole potato, or do they both cook the same? Sliced potato. Now, you take the same, and this is the idea behind French fries, right? Take a potato which is like chunky, making the skinny finger thingies, right? And stick it into boiling oil and like in a few, I don't know how long. Any of you work at McDonald's? How long do you stick it in? How much? 2.5 minutes. Is that right? Okay. So whatever the number, I don't know what the number is, but is that right? 2.5 minutes? Okay. So extra credit too. So if you were to have the whole potato, how long do you think it would get you to cook that whole potato to the same extent that the fries are cooked?
Probably if you can.
That's a good point. You may not be able to. You may like. Yeah.
You'd burn the outside of the potato before you.
That's why you can make fried ice cream.
Oh, extra credit. Good point. Right? Okay. So if you wanted to cook the inside of the potato, you may have to cook it like in a different fashion, right? Like for much longer. So instead of 2.5 minutes, you end up with a baked potato that probably took you 45 minutes or some number in the oven. So that's basically what you've done, is you've increased the surface area to volume ratio. You've given that same potato way more surface area, and the boiling action, like with the oil, the heat is being transferred through the surface. So the more the surface, the quicker the heating, the quicker the cooking, and so on, right? Okay, so make sure that you go and look over these questions, and I'm going to go and stop this particular lecture session here.